Again, this is drawing the map outlining the Android API permission mechanism. I'm Andrew Reiter from Veracode. As you all well know, the Android open source project provides a software stack for mobile devices. Within this stack, they implement an application-based permissioning mechanism. However, as many of you may or may not know, when you get the SDK to develop some apps, there's no permission map included. And by permission map, I mean something that will relate API calls to actually permissions that are required in order to successfully call those calls. And not having this map sort of has a number of effects that I see. And it increases sort of this notion of what is called a permissions gap, or the likelihood of a permissions gap. Also, it increases the possibility of failing the principle of least privilege, and also encourages the possibility of ill-conforming code. It is also sort of my opinion that not having a map increases this overall lack of clarity. With such a large project that Android is, it should be pretty plain and obvious as to what permissions are required for which API calls, and perhaps which API calls require a number of permissions, that kind of thing. So it's in my opinion that having a map would help avoid this permission gap problem, which I'll discuss. It would also help to follow the principle of least privilege that we all in security know well about. Thirdly, it will increase the dev and app security or an app analyst work time. This is because they will have a ready file that will say these are the permissions that an API call can have, and then they can, when they do their analysis for methods being used in an app, they can say, okay, great, they've used all the correct permissions and asked for no more. There have been some prior mapping attempts. Multiple research groups, university-based, have tried with varying degrees of success. And really, as you'll see, there's no sort of one best solution for this problem. And it was the goal of the research of myself and Zach Lanier, formerly of Veracode, to provide a more comprehensive and a reproducible methodology. So I ask you to sort of listen to an overview of permissions and sort of my arguments for why a map would be a good thing to have, and a survey of 4 published automated map generation methods. You should sort of think about who might want to maintain such a map. It is in my argument that Google should. But why aren't they doing that now? And if not Google, who? So I ask you to just sort of think about that. So the API permissions are what are considered at the application level. And this is sort of versus the Unix traditional user-based model. Now, granted, in this, there is some usages of groups and group IDs at the lower levels, but really this is just buried underneath the application schema. Furthermore, this is a fine-grained scoping permissions. That is, you have, say, read-write contacts, read-write bookmarks, that kind of thing, rather than saying, just a general personal information permission. But it actually breaks down further. And in this case, when we're talking about API calls, we're actually talking about like public methods in Android.jar. And that's a generalization, but that's pretty much what we're talking about here. And in terms of permissions, they are just types, they're just strings. If you look at the Android manifest permission class, they're actually just static strings. There are some defined elsewhere, but that's how they're defined. And in this talk, in this research and talk, we're not dealing with intents, and we're not dealing with third-party permissions. As you can see here, if you just hook up your phone or whatever Android device that you have, and you use ADB, you can query the package manager in order to list the permissions that have been registered within the package manager. And for these, we're not dealing with. We're just dealing with the core Android API. So in terms of the permissions lifecycle, you have the developer time. This is when developers writing an app, and they need to use some method from the API, and they say something related to Bluetooth administration. In order to successfully use that API call, they must actually add this Bluetooth admin permission to their Android manifest.xml. And the developer will compile their app and include this Android manifest.xml as deemed necessary. And the user will then attempt to install the application. Of course, this is just Instagram, just to show you the number of permissions that they're requesting. But the idea here is to say that it's install time granting. You accept all or you not install. That's really a key point. And when you accept these permissions and allow the package manager to proceed to install the application of choice, it will register the app's perms in the system, as well as dealing with the group IDs for lower level checking. And then furthermore, in the permissions life, there's the runtime verification and validation of permissions. There's one thing to request permissions at install time, but permissions are actually verified at runtime. And they're verified using a handful of methods that are part of the API. The context object provides a few. Check calling permission, check permission. There's others, enforce calling permission. A number of others, there's about 8. Also, the package manager, as you might suspect, being the thing that deals with packages being installed, also provides such a method. This is check permission, you pass it a permission, you pass it a package name, it'll verify it. And all the locations throughout the API in which you actually do verification of permissions at runtime are what we call permission enforcement points. In this case here, and this is typical, they'll attempt to verify that a permission is had by the calling process. And if it does not have that permission, it'll throw a security exception. That's the typical way to do it, but we'll see that that's not always how it is. And these permission enforcement points can be found throughout the API, but really what we see is that they're actually on the other side of the binder. That is, they're on the service side of the binder. The binder is like a lightweight RPC mechanism. It's a local RPC mechanism since it's all within your device, rather than going outbound to the internet or some other network. And you can see here, you have your application over there on the left, and it's using the Android API. And within the Android API, there's some proxies there for certain methods, such as Bluetooth, things of that nature. And what happens is that you'll call, say, a Bluetooth getName function, and it'll dispatch a call into the binder and asynchronously get picked up by the Bluetooth service and actually execute that call. And during that execution of the call, it'll actually contain a permission enforcement point. And so it's there where it's checking the calling permission and verifying that this app over there was given the Bluetooth permission, something of that nature. So we can actually see this in code. We have the local side of Bluetooth adapter.getName. And you can see that actually there's this, inside of it, there's this return mservice.getName. And this is the dispatch call to the binder. And then we have the service side of the Bluetooth, namely Bluetooth service. And it actually does the context classes enforce calling or self-permission, and it attempts to check it against the Bluetooth permission. And upon success, this will return the get property name. Upon failure, it'll actually be throwing a security exception internally. Aside from the PEPs, there's actually lower level enforcement that occurs, and this is at a Unix group level. When you say OK to accepting the internet permission, for example, with JavaNet socket and the need for inet address, you're actually also putting that application into the inet group. And so what happens is, with the socket support, it's actually wrapped around the native code. And that native code is doing some file system operations and other lower level operating system calls. And here, these actions on the file system and other operating system calls will actually need certain group permissions in order to be called successfully. And so this is why, your activity or app, when it's running, will actually have the effective group ID of INET when it's trying to access sockets and stuff of that nature. You can see sort of the ugliness of the native code if you look at the libcore code that's listed there. And you can see all the mappings of Android permissions to group values if you look at the source tree and look at framework-based data, etc., platform.xml. And so let's do sort of a basic example of a case of where you need permission and the failure versus success. So here I have an onCreate method, which is part of an activity. And basically, I get a handle to the Bluetooth adapter, and I am just attempting to call getName. This getName method requires the Bluetooth permission. Say if I did not provide it, I would get this mess of errors. You'll see, I know this is kind of hard to see, but you'll see here the Java lang security exception, need Bluetooth permission, neither user, blah, nor current process has Android permission Bluetooth. This is the security exception that's thrown on the binder service side. And then it'll actually come back and you'll get another exception, Java lang runtime exception, unable to start activity, blah, 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 Java lang security exception. So you get kind of like a double fault almost, so to speak. Now, if we did have the permission in the Android manifest XML, then we would just have things succeed. If you recall the code here, I just log out to logcat with a name that gets returned. Great. Excuse me. So there are a number of reasons that I believe that we need to have a map. First is this permission gap problem, which I'll get into just in a few moments after this slide. The next is the principle of least privilege. And third is something that I think is extremely important and would take care of a lot of the first two issues, which is if you had a map, you could easily integrate it into an IDE such as Eclipse. So that if you did, Bluetooth adapter getName, and you wrote that in your code, then the IDE would either prompt you to add the permission to your Android manifest.xml, or just would automatically add it. If you removed that method and other methods that required that permission, it would remove it or prompt you to remove it from the Android manifest.xml. Things that would aid the developer so that they weren't getting things incorrect from the beginning. Also, it would be quite useful in security tools, such as those wanting to verify that an app has the permissions requested that are only required of it. If you look at the Black Hat 2012 talk that Zach Lanier and I did, we presented some examples of incorrect documentation and misleading documentation, which also is a good reason for why we want to have a map. If the docs aren't correct, at least something other than that should be a basis for reality. Documentation is well known to all of us to not always be correct, and so why should we be relying on it for something that's so important to a system? I mean, as we all know, security is important. So if we're telling people lies about what permissions are required for what, then we're not really helping the situation. And these other two are quite obvious. So the permission gap problem. Any situation arising when the permissions requested by an application being installed do not match the permissions required by the application being installed. And I sort of like to think about this set theoretically. Let A be an Android app, let P of A be the set of permissions required, P of A be the set of permissions requested in Android manifest.xml of the app A. And P star A be the set of permissions required by app A to run successfully. And as notation, let P1, P2, blah, 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 just be permissions within the system. So essentially, there's 4 granting cases associated with this gap problem. First is the ideal case, in which all of the permissions requested are the exact same as those required by the app to run successfully. You can just verify this by doing commutative set theoretic complement and verify that they both are the null set. The next case, second case, is the overgranting case, which is the most worrisome. And this is when P of A, the app requesting permissions, actually results in having more permissions requested than are actually required. And this is a security issue, which we'll talk about further. Thirdly is undergranting, which is the opposite. Your app doesn't request the permissions required to run successfully the methods used in it. And the fourth, you can have both issues at the same time. And that's just overall a mess. So the undergranting case, which is, I would argue, less issue with security, maybe not, but somewhat, is the basic issue here is usability. If I can't call Bluetooth get names and have it return successfully, then there's a deficiency in my code. I'm expecting to have that get name to build up and use it for something. But if I can't actually get the name, then, well, there's a problem there, usability. And this often leads to what I call chaotic permission adding. And it's basically where a developer is sitting there and they're like, I need to get this code working. Let me get this code working and let me just add every permission under the sun. Bluetooth admin, everything. Access, find location, whatever, just to make sure that the code works and it's usable. And this sort of leads to this overgranting gap, or can. And overgranting, as I had described it set theoretically, is a clear failure of the principle of least privilege. Obviously, you're asking for more permissions than you even need. And so that's quite obvious. And the basic sort of security implications that you might want to think about is, say you're using a third-party library such as an ad library, and your game app requests internet, camera, and read contacts. You have some advertising library that you're using, and in reality, this get and load advert method will actually download some image that you can load and put into your app screen, right? But it notices that you have the camera and read contacts permission. So it's actually going to also, while you're doing the get and load advert, it's also going to do harvest contacts for spam and take pick and send. Now, the thing is that your game, in this case, in this scenario that I'm presenting, your game did not actually need camera or read contacts. You just happened to have them there, perhaps by copying another project or other. And what this does is actually allows them to do some evil, right? And that's kind of hidden underneath what their goal is, which is get and load advert. So obviously, you would want to remove the camera and read contacts issue. Now, if we go back to this, some of the other security implications, I want to point you to this last one, this using other processes privileges. Some interesting work from Adrian Porter-Felt. The paper is listed in the references page, but I highly recommend it. Furthermore, for other permission gaps, the permission gap can occur in the case of copying or pasting old or third-party project. Basically, when I'm writing an app, I always just copy. Usually, I just copy and paste something from before because I usually don't like to use Eclipse. I just like to, use Ant in the command line, stuff like that. So it's easier for me just to copy and paste. And I just wanted to remind you of principle of least privilege. You all know it very well. But the idea is that the app should only be able to access the information and resources that are necessary for basically allowing it to run in a legitimate manner. The map, as I argue, can achieve in this. But this now makes me wonder why there is no map. Well, Google, after having talked to their security team, or the Android security team, deems this a low priority. I'm sure they have plenty of number of other issues on their plate, but they say that this is not one with high priority. I tend to argue a little bit against that, but we have no real say there because we're not part of Google, or I'm not part of Google. Once there had been no map to start with, it's actually kind of difficult to create one, as we're going to see. And if you had one to start with, it's actually a little bit easier to build one out. You can just do diffs between versions, and it would take some hand analysis. But doing the diffs between them, at least you have a baseline to start with, and give the next map that you generate for the next revision some basis of belief. As I stated before, multiple researcher groups have attempted this, but it's a tough problem. So why is it a tough problem? Well, the sheer size of the API. This is huge. And not all permissions are checked in the same manner. Yes, there were the API methods that I presented earlier, but there are other ways that permissions could be checked. And so we have to worry about those when trying to generate this map. Also, check failures are not all handled in the same way. If I were to do a dynamic method for generating this map, I would have to do some log analysis, and with inconsistent logs, well, that's going to be a problem for basing assumption in a tool to actually harvest the permissions out of those logs. And then obviously it's a moving target. Pushing out new API revisions, you're going to have to regenerate a map. There's going to have to be a team or somebody that's always going to be focused on generating this new map. And the last one here is the most important one for everybody, I think, is that there's no kind of ground truth to really test your map to be correct. If there was something that you could say, is my map correct compared to this thing? Well, you'd already have the map. The only way to actually verify things is to know you have good test cases with valid arguments that should run, and then actually run them and verify things work. So in terms of numbers, look at this. The numbers of permissions over API calls, or sorry, over API revisions is ever increasing. Strongly linear, and if we sort of project out to Rev 30, there's going to be over 150 permissions. That's quite a lot, and quite a lot of fine-grainedness and subsystems to be thinking about. Also, there's this ever-increasing class count. There's, was it Rev 10 added NFC and things of that nature. So as more hardware comes out, there's going to be the need for more classes to support that hardware, and therefore more code to analyze. And to really sort of emphasize this is the number of methods that we have here. The blue is actually methods plus constructors, and the red is just methods alone. But if you look at this and you project out to Rev 30, you've got about 36,000 methods that you're going to have to analyze. And then think about different arguments if you're doing it dynamically. Relating to this check analysis issue, say you're doing static analysis to attempt to generate this map. Well, first of all, you have to get a grip on all the API methods, such as those in the context class, and that provided by the package manager, and get a grip on those. And so there's a few there that you need to worry about. But then you also have to worry about these edge cases. Basically, as I told you before, permissions are just strings in Java. And so what can happen is this case here, where they would do this service info object requested from the package manager, and they just do a dot equals to compare this bind wallpaper string to the string that gets returned from SI permission. So that's not like your standard PEP point. It's non-standard, non-conforming to the API. And then lastly, in terms of check analysis, if you have group ID enforcement, there is no check permission call. It's done by the OS and then gets returned up when you hit an error upon verification time. And so, how are you supposed to look for that? Also, other complications. Since these are just strings that we're dealing with, one, in the API code, could conceivably define a local string that's just Android permission, Android manifest permission, Bluetooth, and pass that as an argument to the check permission function. So your code, your analysis code, actually has to be aware of local variables and keeping track of those, not just actual method calls and analyzing the arguments to that. Another real big concern with these check issues is the fact that some API methods logically have multiple permissions that can be associated with them. And they'll be associated in and/or ways. Meaning, you know, if you have the bind wallpaper or the read context permission, you can do something. Or you might need both. And in this case, it's hard with dynamic analysis because you might only test the code to a point where it will return failure on one of the verification points. And so you'll believe that the only permission required for this API call is the one that you first triggered the security exception on. Whereas maybe there's another layer or another layer or two there that you need to get past in order to recognize all of the permissions required. Furthermore, with dynamic analysis is the log message inconsistency. The top, we have a fairly standard output where they have thrown a security exception, and we saw this before with the Bluetooth example. But now below, where we have an app that doesn't request the internet permission, and we actually get a socket exception, and you can actually see the e-access permission denied there, which is coming up from the OS call. And these are totally different from each other. They're totally dissimilar. And from a log harvesting to generate a method to permission, you know, you're going to have, you don't have enough basis of assumption to build a tool in order to help you out with this. Also, a very key important difference is that at least in the Bluetooth case, they're telling you the permission that you need. But here, they're not even telling you. In the bottom case, they're not telling you at all that you need the internet permission, and that's really what you need. And again, in terms of difficulty with results analysis, there's no ground truth. So really what you have to do is say other people that are generating maps, other researchers out there that are generating maps, let's compare them. Let's see how, you know, what our beliefs are together. And if there are differences, maybe hash those out or not. But the problem with this is that they're not all correct. Each method for generating their maps has shortcomings and fallbacks, and if you can't rely on the correctness of them, and you have something incorrect in your map, and you're validating them together, well, they've just double validated and bad permission mapping. So it's a problem. We'll talk about this dynamic side product later. So these numbers of reasons that I went through, the check analysis, the log analysis issues, the numbers problem, is basically why there have been multiple solution attempts to this. People have said, well, if I went about it this way, I'd have this problem. If I went about it this way, I'd have this problem. You know, so they each tried their own. So let's go through some of these. I list these in chronological order according to published date because I'm not trying to give preference to anyone. I think they're all legitimate ideas and worth thinking about and possibly enhancing or merging with some of the others and to come up with a more comprehensive solution. First, we'll go over the Berkeley Method. This is work done under David Wagner and Don Song. Many of you may remember Don Song from, well, a lot of work, but one of the things she did in the early 2000s was looking at SSH connections and basically came up with the idea that, you know, if you look at an SSH connection for long enough, you can begin to recognize patterns and then begin to sort of determine what's going on in that session. And so she was one of the ones that pushed for doing random padding of packets, SSH packets, and that kind of thing to throw off eavesdroppers. This was presented at ACM Computer and Communication and Security 2011. So their approach basically, they will generate an app, or multiple, as you'll see, that calls like every API method within the Android.jar. And it'll do it with varying arguments. And when it creates the APK file, it will put no permissions in the Android manifest.xml. The idea here is that when you call any method that requires a permission, well, you have no permissions requested, and so it should throw a security exception. And from there, they can harvest those from logcat. But the problem is, as we saw, is the log inconsistencies. So basically what they do is they don't specify in their paper exactly how they do it. But the way I would do it is just wrap each API call to catch the security exception and have a nicer output. And the basic flow of how their stuff works, they do this test generation, they run the APK, and then they do a log analysis. In the APK generation, aside from no permissions in the Android manifest.xml, there's a number of steps that require real work. And the first is they analyze the Android.jar to see what they actually should be calling, which methods and things of that nature, as well as they look up types, data types. The reason for this is that in order to call Android methods, you actually need to have arguments to those methods. And they're not all going to be string or int or basic data types. They're going to be more complex object types that are part of the Android API. And so they have to create a variable pool. And that's, so I can say, I need to create test case blah, and I need Android type Bluetooth adapter to keep using that. And well, hey, they have one ready in that pool to be used. So that's great, that's helpful. They must also generate object instantiation code. And this can either come from constructor, as you know, or static methods, where maybe you need to get a handle to a service or a service manager class. And then lastly, they need to generate the method calling code. And in this, they need to have, it is ideal to have varying arguments. And the reason for that is to hopefully test the code well enough so that you can trigger any security exceptions that would occur. Yeah. But this method has some clear drawbacks. The first and foremost is, are they running these APKs with no permissions on an emulator, or are they doing it on hardware? If they're doing it on an emulator, they're clearly not going to handle the Bluetooth stuff. They're clearly not going to handle the NFC cases. So there's issues there. They're going to miss permissions based upon that. So they have to run on hardware. But running on hardware has its own issues, as we all know. Next issue is this code calling and system state. Basically, if you're calling methods within the API, and the first argument to some method is an integer, but really it's expecting some enumerated type from values 0 to 10. But you keep giving it 1024. Well, clearly that's not going to help in terms of actually trying to successfully run the method and actually successfully trying to get to the security exception state. Also, call ordering can be important. If you make one call ahead of another, perhaps that changes the system state so that you have some issues in terms of triggering a security exception. I already mentioned the failure to discover the logical and/or cases. But a major problem here is that they need to test all of these methods in order to verify that they've got all of the security exceptions thrown and can harvest all that data. And there's, at this point, over 29,000. And then you vary those method arguments. That's a lot of test cases to be generating. Of course, they're doing this automatically. However, there are cases where they do it manually. So in terms of availability, they released no code. But they did put up a website, androidpermissions.org, which was housing permission maps that they generated. And they housed them and said they weren't necessarily correct. And we're always offering for people to submit fixes to them. So that doesn't really make you feel very good, even though the people working on the problem are very reliable. But as you can see here, the website's been down. It said it was going to be back July 5th. Yeah, I checked that yesterday, I think, and it's not up. I also saw something on the Berkeley website about some work that was redacted, and I couldn't find a clear website describing what was going on there, but from what I feel is that maybe someone in their own group was like, this isn't really up to snuff, so let's sort of unpublish this. Gives you real faith. So this is sort of an aside to this. It's worth noting that they first tried doing the APK generation using Randoop. Randoop basically is a random Java test generator. You pass it a jar, it'll try to do its best at generating multiple calls to methods within that jar and throw out all sorts of different arguments and generate a whole bunch. I decided to try to do this just to see how it worked. And I have to agree with them. It was very unwieldy. But the biggest problem is that you had to then modify the setup so that you weren't generating just one APK. You were quickly going to hit the method reference limit, which is 64,000 or 64K. It's also JUnit heavy, and it was hard to integrate Android types and hard to control as written in Java. So they wrote their own tool, and as you'll see, I wrote my own tool, or we wrote our own tool. Departing from dynamic analysis, you have the University of Luxembourg and Lille methods, done our work under Leitron and Montperu. This was published on Archive, but I'm not really sure if it was discussed anywhere publicly. They use a forward static analysis approach. Basically, what they do is they say, we're going to build a call graph of the Android.jar, and we're going to attempt to go from all the method calls and try to find the permission enforcement points. And if they can find from a method call, if they find a permission enforcement point, well, they know that that API method requires that permission. And so, sort of a flow graph of what they do. So for each class I, for each method K, go through this whole step of iterating through the tree generated by the entry point that is method K. And they're using this library called Soot, which is an optimization framework. It can be used on Java source, jars, or intermediate representations. The main issues to note is that they must iterate through all the API calls like the dynamic did. The call graph is extremely heavy. And they do not get to the lower level group checks. And it's not clear as to how they mark PEPs in their tree. There's no code available, and they don't release any maps for analysis. The work done by Zach Lanier and myself was in spring of 2002. And basically, it's a hybrid static and dynamic approach. We use source analysis to get a baseline map. And then we generate all these APKs with no permissions in manifest.xml and try to run that and harvest the logs in order to determine what we had missed from our static analysis approach. In our backward static analysis approach, we basically take a look at each PEP point, and then using the tool cscope, which we've modified to better handle Java and the interface description language from Android, and we say, find this symbol, which basically means find all the points in the tree where there's a permission enforcement point. Then we go through each one of those permission enforcement points, and we attempt to find all the methods calling that. Check all those methods. Are any of them API methods? If they are, great, add them to the map. If they're not, continue. Find out which methods are calling that method that isn't an API call. Are any of those API methods? Continue the process out to the graph's edge based from the PEP start. And the thing is it's a lightweight call graph. This is because all we're doing is querying an indexed source index, basically. And there's no just graph with nodes and edges that is loaded into a file. So this is just a description of the thing, of the process and this backward static reaching process. And then we go on and use a dynamic analysis approach. And as I mentioned before, it's a failover. In this case, we'll catch things such as internet because we actually try to create a socket. We actually try to go out and connect to something. This is sort of similar to Berkeley's method. They were the inspiration for this part. We have a variable pool for arguments. We generate calls via Android, the jar analysis, and we put no permissions in Android manifest.xml. And also we generate multiple APKs in order to avoid the method reference limit. So then we take the static and dynamic maps that were generated, and we merge them. And any conflicts, we have to hand analyze. So some basic issues to know with this is that you need the source code. And as anybody who's downloaded the Android source code, it takes time. It takes a while. It's also a two-step process, which might be a little off-putting. Conflicts in map merging is a problem because that then requires manual investigation. And the whole goal with this is to make this automatic. We also don't provide any code, and we don't provide any maps, which I'm not sure I should be laughing about. But anyway. But there are some positives to this. The fact that really, by having this sort of two-sided approach, you're going to reduce your reliance on manual methods over the long term. And as a side benefit of generating these dynamic cases, you're actually generating test cases at the same time. All you need to do is add permissions and validate that things ran okay. So I'm going to mention this and skip over it due to time. The University of Toronto has done a backward-reaching static analysis approach where they use soot to analyze the Android jar binary. Basically what they do is similar to us. They go from the PEP points back to the entry points. So they find all calling methods of a check permission case and compare any of those callings to API methods if they are added to the map, et cetera, iterate through. They actually do publish their code and some maps. P-Scout is pretty good. I've gone through it. It's a little bit complicated, but as many of these are, you're dealing with a large source base, you're dealing with a large jar file, you're dealing with a lot of code. They provide maps for those as of last week, and I'm out of time. So let me just close with this. Dynamic approach to this problem, there's a lot of issues. There's long-term manual work required and increased failure to find permission mappings. But with the static methods, it's a little bit more reliable, but there is some manual work in terms of patching the call graph for the binder, need to handle group permission cases, such as internet, and but the last benefit of the dynamic is that you get these validation test cases for free. So as you can see, it's a mixed bag, right? There are some positives, there are some negatives. Each requires a little bit of manual. Each has its good auto-magically map generation part, but there is always some work. Let me just finish with this. So these two things are the most important part, in my opinion. So what is the solution? Either Google or a stable third-party organization is going to maintain this map. They're going to have to invest in creating the old maps that are valid and mandate that each SDK released has a map. I believe it should just be in the platform's Android rev in that directory. It should look something like this. You have the permission call on the left, and then the API call on the left, and then the permission on the right. Flat file, easily to grep. You can diff it between different versions, that kind of thing. But it's still an open problem. All maps are generated, validated, made public, and funds are there. Until that happens, we're not going to have a real solution to this problem. References are available if you look at the slides online, and thank you. I apologize for running out of time.